situation employs fundamental principles of classic Newtonian mechanics, which presents a thrill to both the skydiver and onlookers. In this video presentation, we aim to explain the physics of skydiving and how a parachute works in this process from a Newtonian perspective. We will provide a brief history of the development of the parachute. We will then mathematically consider and explain the nature of the forces acting on the skydiver and how these ultimately affect velocity and acceleration. Finally, we will investigate how surface area of a parachute affects the magnitude of the resistive force by timing the fall of parachutes with varied radii.
So the idea of the parachute was first conceived in the writings of Leonardo da Vinci. Building on this idea over the 18th century, the French scientist Louis Sebastian Lannemud developed a model essentially consisting of two umbrellas. It was not until 1797 that André Jacques Garnerin designed and completed the first parachute, consisting of a white canvas approximately 7 meters in diameter. Garnerin attached this parachute to a helium balloon which was released at a height of approximately 1 kilometer above the surface of the Earth. While this model marked the genesis of the parachute, its design locked modern features of today's parachute, and as such, it caused the model to jerk violently in its downward motion. Nonetheless, he landed safely, thanks to a remarkable piece of Newtonian mechanics.
To understand the physics of skydiving and parachuting, one must understand the basic concept of a drag force. When an object moves relative in motion with a fluid, for example such as a cricket ball being thrown through the air, it experiences a force known as a drag force. The direction of this force moves opposite into the relative motion, therefore it really moves in the direction in which the fluid flows. The actual magnitude for this force, however, can be defined from equation 1, where C represents the drag constant, rho represents the density of the fluid, A is the cross-sectional area in which perpendicular to the velocity, and V is the velocity at the instant in time in which the object is through.
How does all of this apply to skydiving and parachutes? When a skydiver jumps out of an aeroplane off a high cliff, he falls relative to the air surrounding him. He experiences a downward gravitational force as well as an upward drag force. Acceleration therefore reduces and the skydiver gains velocity at a smaller rate as the drag force gradually approaches the magnitude of the weight. This can be explained mathematically using Newton's second law of motion.
When the magnitude of the upward drag caused by air resistance equals that of the downward gravitational force, the net force of the object becomes zero and the skydiver falls at a constant velocity. Therefore, acceleration is equal to zero. So in accordance with Newton's first law of motion, the velocity known as terminal velocity is the velocity in which a skydiver returns safely to the Earth without suffering the effects of ever increasing velocity.
So how does a parachute help the skydiver? We saw previously that the magnitude of the drag force is directly proportional to the cross-sectional area, which is perpendicular to the relative motion. By opening a parachute during the dive, the surface area is abruptly increased. This rapid increase in surface area increases the magnitude of the drag force, so the diver undergoes a negative acceleration. As the diver falls with the open parachute, he eventually reaches a new terminal velocity, which is smaller in magnitude compared to the initial terminal velocity, which allows him to safely land on Earth. We investigated this effect of surface area on the magnitude of the drag force by timing the fall of parachutes with different radii.
Whoa.